Continuous probability distributions. So in order to take a look at this, these are going to involve continuous random variables, and these variables can take on infinitely many values and they can only be measured. For example, like time or height or weight. Now, a continuous random variable is going to be defined by its probability density function. And in order to make a bit more sense of what's going on, we're going to look at an example we're going to look more at later, but let's draw up something. So we're going to have a piecewise function that is going to look something like this, where we've got a horizontal line along the x-axis here, and then a decaying exponential curve here. Now, this is what we're going to call our probability density function, or PDF for short. And we can only have a probability density function if it's defined where this function f of x is always greater than or equal to 0. And this is the case here because the lowest value for y is y equals 0. So this one is so far satisfying this condition. Another condition for the probability density function is that the integral of the function from minus infinity to infinity with respect to x is going to equal 1. And that has to do with the fact that always all probabilities, always when they're added together, is going to be 1. And what that represents here is that the area under the curve from minus infinity to infinity, well, all of this area over here is 0 in this case. So that means all of this area from 0 to infinity has to be equal to 1. Now, we also, if we want a probability at any point on the x-axis, for example, we can define that by, so we're going to call our continuous random variable x, and if we assign that any value of x, that probability should equal 0. And that should hopefully make sense because if we look at a particular value for x and look at the integral just on that value alone, it has no width. It has no width and that value has to be 0. But as soon as we start defining probabilities that are less than a value of x or greater than a value of x, we then can get some actual values. So for example, if we have a and b, and we wanted to find the integral from a to b of our probability density function, that's going to give us the probability of having a value of x between a and b, which is going to give us the area under the curve in between those values for a and b, and that's how we get our probabilities. And going by this, the fact that on any value the width is equal to 0, it actually doesn't matter if these are less than or equal to or just less than. So all of these statements are equivalent. This will be the same thing as the probability if x is between a and b, not equal to, or equal to just a, greater than or equal to a and less than b, or even just greater than a and less than or equal to b. So all of these are actually just identical because it doesn't matter if it equals them or not because these have a width of 0. So let's go ahead and define a few more things. So if we want the median, let's call it m. This is going to occur if we know the area under this whole curve is 1, we want to know up to what point is the area under the curve equal to 1/2. So our median will be defined as the probability of when x is less than m, and that's just going to equal the integral from -infinity to m of our probability density function when all of this equals 0.5. And by solving for m, we'll be able to find the median here. The mean, which we give the symbol mu, also equal to the expected value of x. This is going to equal the integral from -infinity to infinity x times f of x dx. So it should be median, not medium. Okay, so this is how we're going to get our mean, or our expected value. Now, we also can find the variance, which is going to be sigma squared, or var of x, and that's going to be equal to the expected value of x squared minus the expected value of x all squared. And another way to write that is that the expected value of x squared is another integral, and that's going to be the integral of -infinity to infinity of x squared times our probability density function minus, well, the expected value of x is just the mean, so we could write it as the mean squared. Also, when we're finding our integral of the probability density function, we're finding multiple probabilities all added together. And when we do that, we're actually finding a cumulative distribution function. So every time, when we're finding the integral of f of x, this gives us our cumulative distribution function, or CDF, and we can denote that as big F of x. So we're doing that every time we're finding some integral from -infinity to any value a of f of x dx. And another way to write that is just the probability that x is less than or equal to a. All right, I think it's time we look at an example. So we're going to let the duration of a phone conversation be x, big X. So x is going to be the duration of a phone call, and it's going to be represented by the continuous probability density function, where f of x equals, so it's a piecewise function, and it's the example that we just had just previously that we kind of graphed out of c e to the minus x over 10, and this is defined when x is between 0 and infinity, and 0 for all other values. So we already had a little bit of a look at what that graph might look like, but let's go ahead and answer some questions. So the first thing we want to do is find the value of C. I want to find the value of C. And we know that the area under the curve from minus infinity to infinity has to equal 1. So we can say that the area, and it does have to be from minus infinity to infinity, but we know that the value is 0 on all values other than 0 to infinity, so we don't even have to worry about anything past 0 because its area under the curve will just be 0. So we can actually just look at from 0 to infinity of CE to the minus x on 10 dx, and we know all of this has to equal to 1. So let's go ahead and compute this integral. So we can take C out, and that'll leave us with the integral from 0 to infinity of e to the minus x over 10 dx. Then we can go ahead and find that integral. So the integral of an exponential function is just going to be 1 over minus a tenth times e to the minus x over 10 from infinity to 0. So we're going to have C outside of, now 1 over minus a tenth is just minus 10, e to the minus x over 10, 0 to infinity. So we can go ahead and sub some values in. So let's sub in infinity first. So we've got minus 10 e to the minus infinity over 10 minus 10 e to the minus 0 over 10. Okay, now we're going to have C outside of, now e to the minus infinity over 10, we could think about it as if we have a curve where we have some constant times e to the minus x, we've got this kind of function here. So as x approaches infinity, this function is approaching 0. So this whole term here tends towards 0, and we're left with minus 10, which is 10. Now e to the minus 0 over 10, that's just e to the 0, which is just 1. And we know all of this has to equal 1, because it's our definition for our probability density function. So then just dividing both sides by 10, we get C equals 1/10. And now we have our definition for C in our probability density function. So next part of the question, we're asked to find the value of the probability of a phone call that's less than 2.5 minutes. So that's just the probability that x is less than or equal to 2.5 or less than 2.5. So to do that, we just need to find the integral from 0 to 2.5 of our probability density function with respect to x. So this is going to be from 0 to 2.5 of, we know the value of C is now a tenth, e to the minus x over 10 dx. We can pull the tenth out the front of the integral. So from 0 to 2.5 of e to the minus x over 10 dx. So we get 1 over 10. Now the integral of e to the minus x over 10. So we're going to So 1 over minus a tenth times e to the minus x over 10 from 0 to 2.5. 1 over 10. Now 1 over minus a tenth is just minus 10. E to the minus x over 10, 2.5 to 0. We can pull the minus 10 out the front, and timesing it by a tenth is just going to be minus 1. And let's go ahead and sub in some values. So we'll get e to the minus 2.5 over 10 minus e to the 0. That's going to give us minus outside of e to the minus 2.5 over 10 minus 1. And throwing that in the calculator is just going to give us 0.2214 to 4 decimal places. Sorry, 0.2212 to 4 decimal places. And that's our probability. That's our probability that a phone call is going to go for less than 2.5 minutes. All right, what about the probability that a phone call will go for greater than 6.4 minutes? So to do this, we could do it in a few ways. So we're after the probability that a phone call will go for greater than 6.4 minutes. We could do this as the integral from 6.4 to infinity of our probability density function, or we could look at 1 minus the probability that x is less than 6.4, which means we'd be after 1 minus the integral from 0 to 6.4 of our probability density function. Let's go ahead and do 1 minus, since we were talking about it. So we'd have the integral from 0 to 6.4 of our probability density function, which is a tenth e to the minus x over 10 dx. And we've already done this quite a few times. So we're going to get something like, well, let's just go ahead and do it. So we can pull the tenth out the front, 0 to 6.4 of e to the minus x over 10 dx. So let's go ahead and find the integral. So finding the integral of this, we're going to get minus 10 after you do 1 over minus a tenth, e to the minus x over 10 from 0 to 6.4. We're going to have, we could pull the minus 10 out the front, so it's going to make it positive 1. So we're going to have 1 plus this answer here. And let's go ahead and sub in some values. So we're going to get e to the minus 6.4 over 10 minus e to the 0, which is going to give us 1 plus e to the minus 6.4 over 10 minus 1. These ones are going to cancel out. So we're just going to get e to the minus 6.4 over 10. And that's going to be 0.5273 to 4 decimal places. And that's going to be the probability the phone call is going to go for greater than 6.4 minutes. So let's have a look at another example. What's the probability the phone call is going to go for between 2.5 and 6.4 minutes? So this time we're after the probability that a phone call is going to go for between 2.5 and 6.4 minutes. So if we can imagine our probability density function, we're looking at the values. We want to know between 2.5 and 6.4. So we're after just the integral between 2.5 and 6.4 of our probability density function. That's going to tell us what's the probability between 2.5 and 6.4. So in order to do that, that's just going to be the probability of, well, that's just going to be the integral from 0 to 6.4 of our probability density function minus the integral from 0 to 2.5 of our probability density function. And we've already found those. We found the integral of 0 to 6.4 as 0.5273 minus the integral from 0 to 2.5 we found as 0.2212, and this is going to give us 0.2515 to 4 decimal places of, and that's going to tell us the probability of a phone call lasting between 2.5 and 6.4 minutes. All right, next question. We're after the mean phone call duration. The mean phone call duration. This. Okay. Now, we know the mean is represented by the integral from 0 to infinity of x times f of x dx. This integral is a bit tricky to find, so I'm going to give you the fact that the integral of x times e to the kx dx equals 1 over k e to the kx outside of x minus 1 over k. So we know, I'm going to give you this integral so we can go ahead and do it. So let's go ahead and try and find our mean from here. So we have the mean of the integral from 0 to infinity of x times our probability density function, which is 1 over 10 e to the minus x over 10 dx. Now, we know we have this integral to use, so let's pull out a tenth first of all. So this is going to be a tenth outside of 0 to infinity of x e to the minus a tenth x dx. And here we can see that we have a very similar integral here and here. So obviously the value of k must be a tenth. So we're going to be using k is equal to 1 minus a tenth. And we can go ahead and sub that in. So we know all of this. We're going to have the tenth out the front times now the integral we know is going to be 1 over k, which is minus a tenth, times e to the k, which is minus a tenth, x outside of x minus 1 over k, which is minus a tenth. We're going to have that integral from 0 to infinity. So let's tidy this up. We're going to have 1 on 10 outside of 1 over minus a tenth is just minus 10. E to the minus a tenth of x outside of x. Now minus minus will turn into a plus, and 1 over 1/10 is just 10 from 0 to infinity. We can pull the minus 10 out the front, so we'll just get minus. And let's go ahead and sub in some values. So minus 10 has come out the front, so we're going to have e to the minus 1/10 times infinity outside of infinity plus 10 minus e to the minus 10th times 0 outside of 0 plus 10. see if we can go ahead and simplify this. So minus outside of now, e to the minus a tenth times infinity is just 0. And 0 times this bracket here is just going to be 0. So all of that actually just equals 0. So we're left with minus e to the minus a tenth times 0 is all just going to be 1. Outside of 0 plus 10, which is 10. And then minus minus turns into a plus, and 1 times 10 is 10. So we get our mean phone call duration as 10. So 10 minutes. So next question, we're after the variance. And the variance is equal to sigma squared, which equals the expected value of x squared minus the expected value of x all squared. So we've already got this value for the mean. We just need this value here to find our variance. And we know that the expected value of x all squared equals the integral from 0 to infinity of x squared times our probability density function dx. This can be a tricky integral to find, so the integral going to give the fact that the integral of x squared e to the kx equals 1 over k e to the kx, all outside of x squared minus 2x over k plus 2 over k squared. So we're going to go integral from 0 to infinity of x squared times our probability density function, which is a tenth, e to the minus a tenth x dx. Let's go ahead and pull a tenth outside of the integral. So we have a tenth from 0 to infinity of x squared e to the minus 1/10 of x dx. And this is in the form now that we need because we know this integral. And k will equal minus a tenth. So we're going to use k equals minus a tenth, and we can plug everything into the integral. So we're going to still have our tenth outside. Now we know all this integral equals 1 over k, which is minus a tenth, times e to the k, so minus a tenth x, outside of x squared, minus 2x over k, which is minus a tenth, plus 2 over k squared, so minus a tenth squared. And all of that between 0 and infinity. So we can tidy this up. So we're going to have a tenth outside of 1 over minus a tenth is going to be minus 10. E to the minus a tenth x outside of x squared. Now minus minus will turn into a plus. And 2x over a tenth is just going to be 20x. Now, minus a tenth squared is just going to be 1 on 100, positive 1 on 100, and 2 over 1 over 100 will just be plus 200. And all of that between 0 and infinity. We can pull the minus a tenth out. So we'll just have minus. And let's go ahead and plug in some values. So we're going to get e to the minus a tenth times infinity, outside of infinity squared, plus 20 times infinity, plus 200, minus e to the minus a tenth times 0, outside of 0 squared, plus 20 times 0, plus 200. So we know that e to the infinity is going to tend towards, e to the negative infinity is going to tend towards 0, and 0 times all of this will be 0. So all of that's 0. we're going to have the minus outside of minus, fit this minus. Then e to the 0 is just going to be 1. Outside of 0 plus 200 is 200. Minus minus turns into a plus, and 1 times 200 is 200. So that's our value for the expected value of x squared. We can now work out our variance, which is sigma squared. It's going to be expected value of x squared, which you just found to be 200, minus our expected value of x, which is just the mean squared. And we found the mean to be 10, so it's just going to be minus 10 squared, which is 200 minus 100, which is 100 for the variance. So we've got a variance of 200 here. Next question is to find the standard deviation. Which is easy when you've just found the variance, because all you need to do is take the square root of both sides, so they cancel out, and we get the standard deviation equaling 10. All right, last question. We're after the median phone call duration. The median phone call duration. Now, we know the median occurs when the integral from 0 to some value, let's call it m, of our probability density function equals 0.5. So we're going to have the integral from 0 to m of a tenth e to the minus a tenth x dx. We need it equaling 0.5. So let's go ahead and pull the tenth out. Integral from 0 to m of e to the minus 1/10 x dx equaling 0.5. Let's times both sides by 10 and start doing the integral. So the integral of e to the minus a tenth x, done this quite a lot of times, so it's 1 over minus a tenth e to the minus a tenth x from 0 to m, and after timesing both sides by 10, we're going to get this equals 5. Let's go ahead and sub some values in. Well, 1 over minus a tenth is just minus 10. Then we're going to go e to the minus a tenth m minus 10 e to the minus a tenth of 0. We know it's got to equal 5. So we're getting minus 10 e to the minus 10 of m plus 10, and e to the 0 is just 1. So we get that. Now let's minus 10 from both sides. So we're just going to be left with minus 10 e to the minus a tenth of m equaling minus 5. Divide both sides by minus 10. So we've got e to the minus a tenth m equaling a half. Take the natural log of both sides. So we're going to have ln of e to the minus a tenth m equaling the natural log of a half. The power will come to the front, so we get minus a tenth m times ln of e, which is just 1, equaling ln of a half. Dividing both sides by minus a tenth, or timesing both sides by negative 10, is just going to give us negative 10 ln of a half. And that's going to give us a value for the median of 6.9315 to 4 decimal places. And that will be the median phone call duration.